Hi everyone. Today we're going to take a look at some applications of integration, some ways that we can use integrals. Today is probably not going to feel like too much of a stretch beyond things that we've already learned. We're kind of just, throwing two functions on a graph at one time. But then, of course, we're going to build on this later on. So really important that you make sure you understand the basics here before we move forward. So, okay, I'm going to I think, just jump into this first example, and then you'll maybe see where this formula is coming from as we talk about it. So first example says, find the area enclosed by these curves. And so I want to just sketch you a graph of what it is that we're talking about here. And again, that'll kind of tie back to like, what is this whole lesson about, right? So we've got this graph. Okay. I could probably make it go a little negative, although we're not going to be looking at anything negative. The first graph is y equals x squared. So we all know what that looks like, right? This is x squared. It's a parabola. And then 2x plus 3, that's a linear function. Slope is 2, y-intercept is 3. So we'll just say that's our 3, and then our slope takes us something like, oh, pretend that's a straight line. Sorry about that terrible picture. Let's see if we can fix that up. Okay, so here's my parabola. Probably better to just do one of these, right? Okay, still not the straightest, but that's my 2x plus 3. So what we are trying to find right now is the area that's like squished between those graphs. So we want to find this area here. That is the point of this question, okay? So we know that we could integrate under that straight line from, let's say, this point here to this point here. I guess I said those backwards. And that would give me like all of this area, right? It's almost like a triangle here. Well, I guess it would be a trapezoid because this shouldn't be right on the ground. But so I could find that area. But I don't want that whole thing. I want to get rid of this area that's underneath the parabola, right? And so the idea here is that I'm going to integrate each one of these functions and then subtract them. Because if I take the area under the line and then I subtract this area under the parabola, I'll be left with just this little wedge in between. Okay, so that's the idea, is I want to do an integral. And if I'm integrating, two functions separately but subtracting, I can just combine them into one integral, and that's where this comes from. I'm going to come back to my endpoints here in a second, but what I have going on here is I have the function 2x plus 3. That's my first function. And then I want to subtract the function that's underneath it, x squared. And so again, I could give these each their own separate integral, but ultimately I'm going to end up combining them so that I don't have to do two separate antiderivatives and all of that stuff. Okay, let's chat for a minute about these endpoints, because sometimes we have to find these algebraically. If we had Desmos available, I would just be looking at those on Desmos. But if you had to find these by hand, you'd be asking yourselves, well, when are these two functions equal to each other, right? So I'm going to go off to the side here and just take a second and find my endpoints. And I'm doing that by making x squared equal 2x plus 3. Well, that's a quadratic, so I'm going to solve it by swinging everything to the left side. And then I've asked you this question a lot this year. If I handed you this thing and said, hey, solve this without a calculator, what would we do? Well, we'd factor. Hope that's what you're saying. We need to multiply to -3 and add to -2. So I would propose a -3 and a +1. And that means my roots are +3 and -1. And that should make sense with the graph that I have drawn. But this here, like I said, that really shouldn't be right on the y-axis, but I'm sorry, the x-axis. That's at -1. This is at 3. So those are my bounds of integration, -1 to 3. Okay, I'm going to go ahead and do this one by hand. I'm not going to do all of these by hand because I do trust that by now you can calculate integrals by hand if you have to. So I'll do a couple and then we'll head over to Desmos. Really, this is not the focus for this section. So first thing I would do, and I would do it over here, except I drew my graph here, is I need an antiderivative. So my antiderivative would be x squared plus 3x minus 1/3 x cubed. That's the x squared. And then I'm putting my endpoint. So pay attention to how I'm showing my work here. Again, ideally, I would just keep working over here, but I'm going to just jump down a line. Oh, and I'm sorry, that's not a 2. It's late at night. I'm sorry about this, guys. This should be a 3. Okay, because it's those endpoints there. So let's start with the 3. 3 squared is 9. Then I have 3 times 3, so that's another 9. And then I have minus 1/3 times 3 cubed, which is 27. That's going to be another 9, but I'll deal with that in a second. Minus, okay, negative 1 squared is positive 1. 3 times negative 1 is negative 3. And then negative 1/3 times negative 1 cubed, that's going to leave me with 1/3 times negative 1. Okay, I'm going to have one tiny annoying little fraction in there. Okay, we said this 1/3 times 27 is really just another 9, right? And then really I have a 9 minus 9, so those just cancel each other out. So I'm left with just this 9 here. I have 9 minus 1, which is 8, and then minus negative 3, so that's really like a plus 3. So I think that leaves me with 11. And then negative 1/3 times negative 1 would be a positive 1/3. Okay. Oh, you know what though? Sorry about that. It would be a positive 1/3, but I forgot this negative sign in front, so it is a minus 1/3. So minus, 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 3 negatives brings you back to a negative. And so 11 minus 1/3, I mean, you could write this as like 10 and 2/3, right? If we turned 11 into a common denominator, it would be 33/3. And so then I would write my final answer as 32/3. So that's the idea, is that we are going to find area that's squished between two functions by integrating the difference between the two functions. Okay, now there's a lot of examples here. So there's a lot of kind of unique situations we're going to run into, but that is the main idea. Okay, I'm going to make you do one more by hand because I'm mean and I want to make you do some trigonometry. And then we're going to jump over and do a bunch of this on Desmos. So with this one, and I am going to pull this up on Desmos eventually, but I want you to see that, like, sometimes we don't know what these graphs look like. I mean, we should have an idea of what sine of x looks like. I'm not sure if you know what secant squared is going to look like, but this one gives me an interval, so I don't even really have to worry about, like, where are my intersection points, because this is telling me my endpoints, right? The 0 and the pi/4. So I'm just going to jump right into setting up my integral. And I'm going to say I want to integrate from 0 to pi/4. Now, I don't necessarily know which order I'm supposed to be subtracting these two in. I'm just going to write one down and then I want to talk about that. But so I'm just going to say secant squared of x minus sine of x dx. Okay, so let's think about what would happen, like worst case scenario, if we didn't subtract in the right order. Think about this one we did up here. What if we had done the parabola minus the line? What should have happened to our answer? Well, really everything else should have worked out the same, except this answer would come out negative. If you're talking about area is never going to be negative, at least not in this context, because we're talking about literal area, like finding area of a triangle or whatever. So if you do one of these problems and your answer works out to be negative, you are just going to say to yourself, whoops, I meant for that to come out positive. And the way you fix that is just by wrapping your work, your integral setup, in absolute value. That's your way of saying, hey, I don't care if this thing comes out negative. We're going to treat it like it's positive. So it wouldn't hurt me to leave that here. I'm trying to just not clutter up my work too much for you. I'm pretty sure this is going to work out correctly. But again, if this came out negative, that's how I would course correct. I wouldn't go back and start over. I would just say, oops, I meant to make this all positive. Okay, We need an antiderivative here. I have faith in us. Antiderivative of secant squared is tangent minus. Antiderivative of sine is negative cosine. Since I already have this negative sitting here, we're going to make that a plus cosine. And our endpoints are 0 and pi over 4. Okay. And so now what I'm doing is tangent of pi over 4 plus cosine of pi over 4 minus tangent of 0 plus cosine of 0. Okay, bust out your unit circles here. I would recommend you pause the video and see if you can do this one on your own. Okay, because this is definitely trig that should be within your grasp. Tangent at pi over 4 is just equal to 1. Okay, I promise you. If you need to draw out the circle, go ahead and do it. Cosine of pi over 4. Pi over 4 is where the x and y coordinates are exactly the same. And that's square root of 2 over 2. Minus, okay, tangent of 0 is 0. Plus cosine of 0, think about that carefully, at 0 degrees, or sorry, 0 radians, the x coordinate is 1. Okay, what I am seeing here is, first of all, nobody cares about the 0. And then I have a 1 minus 1. And so really, this is just my answer. Square root of 2 over 2. Okay, so I'm going to hop over to Desmos and show you how I could tackle a problem like this one using Desmos, especially if it's a graph that you're unfamiliar with. So let's see. Okay, I want you to notice that I'm naming the function f of x. There's a reason for that. So there's the secant squared function. G of x is the sine function. And so what I would probably do right now on my paper is identify which one is f and which one is g, right? If I'm going to name these things, I need to say which one is f, which one's g. Okay, and so you'll notice these functions don't actually even touch each other. That's why this problem had to give me endpoints, because it doesn't, there's no intersections, there's no natural endpoints here. We have to kind of create them. So I am going to modify my graph a little bit. I'm going to use these curly brackets, and I'm going to do a domain restriction using inequality notation. So that's me saying I only want to see this graph between 0 and pi over 4. It doesn't use the interval notation that we're used to in calculus. It uses this inequality notation, but that gives it a start point and an end point. And actually, I'm probably just going to copy paste that down here. And so this is really what we're dealing with, is like the space between the red line and the blue line. If you kind of picture drawing in vertical lines at 0, and then this endpoint here would be at pi over 4, it's that space in between there. Okay, so let's think about the first thing we wrote down on our paper. We said we wanted to integrate, and we knew it was from 0 to pi over 4. And then essentially, I want to do the red graph minus the blue graph, right? So that's f minus g. So I'm just going to, because I named these in Desmos already, I'm just going to type in f of x minus g of x, and then go out here for my dx. And this is the decimal that I get. Now, you might not recognize that. I recognize it because I use these numbers all the time. That is square root of 2 over 2. Don't believe me? Let's check. Square root 2 divided by 2. And that's what that looks like. So, and that's the answer that we got when we did it by hand. So I want you to see that, like, Desmos is fair game here. Okay, speaking of Desmos, example 3, if you're still looking at your notes here, let me clear this off of here, says find the area between these two functions using your calculator. So let's talk about how to do this like completely on the calculator and then what we would write down. So we have the functions. Again, I'm going to name these f of x and g of x. I'm going to mark that on my paper here in a second. Make this x to the power of 1/3. And then the other function is g of x equals x squared minus 3. Okay. So the area we're trying to find is the area that's like squished between the blue graph and the red graph. So you can see that's kind of like this area right here. If I wanted to get really fancy with Desmos, I could do some shading and figure that out. But the first thing we care about is where are these endpoints, right? So my endpoints here, if I click right on the graph, I can find these intersection points. These other ones that are lighting up are just like intercepts. But these are my two numbers that I want to work with, the x values. So negative 1.374 and 2.067. Here's a trick you can do in Desmos if you want to just save these numbers, because as soon as I click over here, those are going to disappear. These little check boxes will bring those points over into your expression list. Now, it's actually only the x values that I'm going to care about here in a second, but I will again do some copy pasting here. So I'm going to say I want to integrate from this negative number here, this x number. So copy paste there, up to this x number. Again, we're just using the x values here. And I want to say, let me just show you what would happen here. Let's suppose I did this backwards. Let's suppose I did g of x minus f of x dx. You'll notice that I get a negative answer, okay? So if I had typed it in that way and gotten that answer, I wouldn't like throw in the towel and just scrap my work completely. Let me go back to our video here and show you how I would write this down. So again, I would probably start by defining like f of x is x to the 1/3. And g of x is x squared minus 3. And then from there on out, for the rest of this problem, I'm going to just refer to these as f and g. I'm not going to rewrite the function at all. So as far as showing my work goes, I would say, hey, what I'm doing is I'm integrating. I do want to make sure I show my endpoints really clearly. When I did the calculation, I used the entire decimal because that's the most accurate. When I write it down on my paper, I want to follow our 3 decimal point rule. So negative 1.374 up to 2.067. Now, what I typed in here was g of x minus f of x. Now, you're probably screaming at me like, duh, obviously from the picture, we could tell that f was on top. And that's absolutely true. I just wanted you to show you what to do if you run into this situation. We saw that our answer came out negative, and so what I would do to communicate the fact that I need to change my answer to be positive is I would just wrap this whole thing in some absolute value bars. And that's me saying, hey, even if this came out negative, I'm going to turn it positive. And then I would just say my answer is positive 7.344. And that's it. That's all you have to show as far as work goes. You can let Desmos do all the heavy lifting. So unless it tells you you have to do it by hand, setting up the integral and then evaluating with Desmos is totally fair game. Okay, I think I'm going to jump into a second video just because this is getting kind of long to cover the last few examples because those get into some other ways that we can use integration. But this should be enough to get you started.